Hello, let's do the New York Times Hard Sudoku for May 6, 2025. There's a link in the description if you'd like to try the puzzle yourself, and I'm going to get started right now. All right, let's look for geometry here. We already have a candidate here, 3, 4, 8 in this row. Unfortunately, yeah, the only thing I'm seeing is we have 8 here, and so actually, we can place 8 in this box. Let's do that. So we can place 8 in the box, and then that does mean 8's over here, which is what I was going to mark. The 3 is also over here. So it does not mean this is a 4, but it does mean it's quite limited. So it's not 1, it could be 2. It's not 3, it could be 4. It's not 5, it could be 6. It's not 7, 8. Wait, why is that so many options? Never mind, it's not as limited as I thought. Yeah, I was thinking about that wrong. There is another digit, a fourth digit that goes in these 4 cells, but we don't know what the fourth digit is, so there's still quite a few options. All right. 3, 4, 8 this way. It's only 3 and 8. Okay, we've got a lot of 8s in this puzzle already. So let's just look at 8s and see if we can just finish them. I don't know that we can finish them. Yeah, so what we've got is 8s here and here. Whoops. And this doesn't resolve on its own. All right. I think that's what we get. We also have 5 and 1 looking through here. So the 5s do match up, putting a 5 in one of these two. That's going to point down with this 5. This 5 looks in and this 5 looks in. So now this is the only place for 5 in the box. Okay. 7, 8, 5. All right. 5, 1, and 3. Okay, so we have 1, 3, and 5 to place in these 4. Okay. 5 is limited. I mean, it's just down here. Doesn't really do much. Okay. We're not doing normal scans. We're doing geometry. Sorry, I'm seeing things, but let's just get the geometry pass done. So 6, 7, 9. Here's your typical New York Times trick right here. I'm looking at these digits. So we have 6, 7, and 9 in this box. They are not yet placed in this column. Where can they go? Well, they can't repeat in the box, and they can't go on top of 3, 4, or 8. So there's only 3 cells left for 6, 7, and 9. So those 3 cells must be from 6, 7, 9 only, so that we place all 3 of them in the column. We can clean that up a little bit. And so that leaves a pair behind here. It's just the 1 and the 2 that are left. And it leaves a pair here as well. It's going to be the 3 and the 4. So this 4 tells us this is 3 and this is 4. Very nice. We'll scan this in a moment. I want to look at 5, 7, 8 here. So we do need 7 in this row. Yeah, so where do 7 and 8 go in this row? They go over here. Right, so this is a 7, 8 hidden pair. That leaves a triple here. We need the 1, 3, and 4. And this can't be 1 or 3, so it must be 4. Okay, we're getting a lot just from this initial glance through the puzzle. 5 and 9 need to go here. So we know the 9's up here. And then the 5, not so lucky. 5's in one of these two. All right. I think this stack we'll take care of in a moment. Is there anything with these? I don't think so. 6 and 9. I mean, we have the 6s. But anyway. There's a lot to scan here. I'm just going to go in order just because there's so much going on. Actually, you know what? I'm going to start with this stack. And then I'm going to do this band. I think that we can get a lot more info out of it. So I'm going to actually start with this column and see if anything's going on with it. We need 1, 2, 3, and 6. So we know the 3 is not up here. So this is 1, 2, 6. And that's not 6. That's not 1. These are 1, 2, 3, 6. We know the 3 is down here. Okay, not too much from that. The 6 looks up here. This 6 looks in. 6 is in one of these two. And so that does mean 6 is in one of these two. Now, where does 6 go in this column? Well, it's not here. It's not in any of these. The 6 is here. It's in one of these two. This is going to do what's called claiming. It claims the box. This column needs a 6. It's in one of these two cells. Wherever it ends up, it will also be the 6 for box 8, kind of coincidentally. And so the rest of box 8 can't have a 6 in it. So that's important. 6 is in one of these 3. In fact, this is a triple. Let's fill that. I know I'm all over the place, but there's a lot of low-hanging fruit here that I want to look at. The 9 looks in. It places the 9. And we're left with 2, 6 pair. This 2-6 pair does look left, making this a 1 and that a 2. Because this can't be 2 anymore. So this row, it just has a, oh, and this can't be 6 because of the 2-6 pair. So that's our 6. We can finish this row with a 1. These two digits are the 3, 4, and this 4 tells us the order. So that's not a 3. This is not 3, 8, 9, no. Okay. Geez, I've gotten so much that I don't I think I should just make sure I get my normal scan done. So 3 here, we have it marked here and here. The 4, we have a bunch of 4s looking into this box. So 4 is on one of these two. I feel like these two cells are quite limited, but we'll get there. 3, 4, 8. Hold on, 4 vertically is good, 8 vertically is good, 8 over, yeah, we already looked at 8s, that's right. So 1, 3, and 5. So the 2 1s look in here, putting a 1 in one of these two. The 3, we don't get much from. Okay, the 5, no. We do have 2, 5. Oh, we have it marked down here already. So that was the 1, 3, 5. The 1 and the 6 here. The 1 is in one of these two. Where's 1 in this row? It's not in any of these cells. Unfortunately, that doesn't do much. Okay. Anything else in this band to look at? Any low-hanging fruit? Not really. I want to look at these two cells, though. Look at all these corner marks we have. What can these be? They can't be 1. They could be 2. They can't be 3, 4. This could be 5. This could be... Oh, neither can be 6. There's a 6 in the box. I was seeing this 6. We can have 7 and 9. Well, neither of them could be 9, right? So we can be 7, but that's it. Right, so we're 7 in this column. Wait, is that a question we can ask? No, it's not. For some reason I was thinking 7s were limited here, but they're not. This could be 2, 5. Okay. Well, let's move on here. Let's just look at this bottom band next, actually. So we have these two 4s. This 4 looks down. That places this 4. These 4s look up. Putting a 4 in one of these two. The 5. I'm not seeing anything with 5. The 8s we already looked at. And then 6 and 9. So... All right, what can I look at here? I think I covered it. All right, low-hanging fruit. We know this is 1, 2, 3, 6, but it's not limited. This cell here isn't a bunch of digits. It's not the 1, 5, 6, 3, 4, 8. So it could be 2. It's not 3, 4, 5, 6. Could be 7. It's not 8. Could be 9. 2, 7, 9. This cell's also limited. It's not the 4 and 6 in addition to the 1, 3, 5, 8. So in fact, this whole column is down to 4. So we should do the whole column at once. We need 2, 6, 7, 9. So this is 2, 7, 9. This is also 2, 7, 9. This is 2, 6, 7. And this is any of them. We have a 7, 9 and a 2, 7, 9 here. So we could look in this row to see if we happen to have a triple. One of the nice ways to do that is to think about what are the digits we haven't seen yet in all of these cells. So we haven't seen the 1 or the 3, and that's it. So the question is, where do 1 and 3 go in the row? And look, we actually do find it, because this cell here can't be 1 or 3. So the way we found our hidden 1, 3 pair in this row, and in fact 3 is hidden, 3, this is the only place for 3, but even ignoring that, the way we found the hidden 1, 3 pair in the row is by thinking about what digits we haven't encountered in all of these cells yet. None of them could be 1, none of them can be 3. And then this cell also can't be 1, 3 after an inspection. So the 1, 3 go here, and this 3 tells us the 3 can't actually go there. So 3 in this row is only here, placing this 1 and also placing 1 in this row here. So that was for the row. Now these ones look in, putting a 1 in one of these two. This 3 looks up, and now we can actually place 3 in the box. When we do so, we remove a 4 corner mark and an 8 corner mark. Now there's only one place for 4 in the box. Unfortunately, there's still 2 places for 8. This 4 removes this 4, placing the 4 here. This 1 removed this 1, placing the 1 in the box. Very nice. This is now down to 2, 3, 6, which we can mark. Remember we had the claiming 6s. I'm just reminding myself. This can't be 2, so it's 7, 9. So, oh, actually, first of all, what we can say is the 2 in the row goes here. So that's not a 2. And then now the 9 can't go here, so the 9's there, and that's a 7. All right. That's not 9, that's not 2. This is 6, 7, 9. All right. Lots of low-hanging fruit. This is 2, 7, 8. These in this column are 5, 8, 9. It's not 5, that's not 8, that's not 9. In this box, we need 2, 5, 8. So we know the 2's in one of these two. That's going to point up. This can't be 2. Okay. 2's here. What am I missing? I'm sure it's something easy. Over here, we need a 2, 5, 7, 9. I mean, I think this can be any of 2, 5, 7, 9. I think that's this whole column. This can't be 5 or 9, though, so this is 2, 7. But this can't be 7, so it's 2, 5, 9. This one can't be 5 either. Oh, what am I looking for here? I might just have to pencil more. This was 2, 5, 7, 9. This is also 2, 5, 7, 9. These aren't 5. Okay, this box is 2, 6, 7, 9. We can mark that, 2, 6, 7, 9. This sees a 7, this sees a 9. So we have 2, 6 here. So this is something I'm going to talk about, but I'm not going to use. We can make what's called a uniqueness deduction here. Uniqueness is a class of actually a fairly large number of techniques where if you assume there's only one solution to the puzzle, which is a fair assumption for something like a New York Times Sudoku, all of their published puzzles have always had only one solution. It's kind of a requirement for a good Sudoku that you can solve logically. So if you're expecting to be able to solve it logically, it's fine to also expect that there's only one unique solution. I don't like adding that assumption because I like myself to prove that there was a unique solution. It's kind of a me thing. So I prefer not to use uniqueness. Also, it's never necessary to use uniqueness in these New York Times puzzles. But we could use uniqueness here because what we've got going here is this is called a unique rectangle. It's kind of the simplest uniqueness deduction. Now, what you need to make sure is that the digits you're looking at are in exactly 2 rows, exactly 2 columns, and this is an important bit, exactly 2 boxes. If it crosses 4 boxes, you can't do it. That's the most common mistake, is thinking you found a unique rectangle, but they touch 4 boxes. All right, so we do meet that requirement. Now, what we need to avoid is exactly this. We need to avoid this being 2, 6 with 2, 6. Because this would cause there to be at least 2 solutions. Because this could resolve with 2's here and 6's here, or it could resolve the other way with 6's here and 2's here. Basically, you could swap them. And that would not affect any of the other digits in the Sudoku. They would both be valid solutions. If you think about it, we've got a 2, 6 pair in the columns, we got a 2, 6 pair in the rows, and we got a 2, 6 pair in the boxes. So there's not going to be any 2's or 6's that are going to tell us how this resolve. So they could resolve either way, and they would be 2 valid solutions. So we need to avoid that, which means, but we know that the 6 has been limited to these 2 cells. So if I also tried to put a 2 in either of these cells, we would cause that, which means we can't put a 2 in either of these cells. We can eliminate the 2 and then place that 2. So that would be a uniqueness deduction. So what I'm going to do is I'm actually going to purple this and say this is going to be a 2. Just remember purple is 2. So anyway, that's my prediction based on uniqueness. All right. What can we do that isn't uniqueness? Let's see. This cell here isn't a bunch of digits, so let's take a look. It's not 1, 2. Could be 3. It's not 4, 5, 6. Could be 7. Could be 9. Oop, not 9. Where's the 9? Oh, it's right there. So 3, 7 only. Have we accounted for all the digits here? 1, 3, 6. 1, 2, 3, 6, 7. Yeah. there's not like a great place to look here. Did I miss something obvious? I could pencil the rest. Let's see. We need 1, 3, 1, 3, 5, 6, 7, 9. The 9 is interesting, isn't it? Yeah, 9's in one of these two. So this might be limited enough. This could be 1. It's not 2. It could be 3. It's not 4. It can't be 5, 6 because of the corner marks here we got here. Could be 7, and it's not 8 or 9. So that does make a 1, 3, 7 triple in this column. So 1, 3, and 7 go here. Another way to think about this is the other side of the coin is the hidden pair. Where do 2 and 6 go in this column? They aren't here, so they have to go here. Either way, this can't be 7. Traditionally, you'd say the 1, 3, 7 eliminates that. And so what really important deduction from this, which I actually saw from just the 1, 3, 7 triple, is the 7 can't go here. So where does the 7 go in the column? It's in one of these two, and that's going to claim the column. Sorry, it's going to claim the box. So if the 7's in one of these two for the column, it can't be over here or here. Well, these couldn't be 7 anyway, but anyway, we can eliminate 7 from these two, and that makes this 6 and 9, making this a 7, placing the 7 in the box. That gives us the 7 up here. We get the, was that the only place for 7? Oh, I just eliminated it. All right, so that's 6 and 2. All right, let's clean this up a little bit. This places the 2 in the box, giving us the 6 and the 9. There you go. Now that's, our purple is a 2. There you go. 6 and 2. That's not 7. This is our 3, 6 and 2. This is our 1 and 3. That's our 1. That's our 5, 8 and 2. That's our 7, 8 and 9. That's a 5, 7 and 8, 5. Over here we get the 7 and the 5. All right, this is the 3. This is the 9. We're done. All right, cool. And notice this did not end up being the pattern that I talked about, right? We have the 2s and the 6s, but this ends up being a 9, not a 2. The only way to disrupt something like this is to have a given placed in one of these cells. Then you can do it, but then there's a given, so you don't look for unique rectangles that have givens. Basically, is what I'm saying. So let me see if I can find an example in the grid really quickly. Sometimes I find it quickly, sometimes it takes some time, but 3, 6, 3, 1, 5, 8. There always is some. Yeah, here we go. So right here in blue. Blue is hard to read over the blue. Yellow. I'll get rid of these. So this would have been a unique rectangle had we not been given this 8, right? The only way this ends up in the grid, in our solution, is by giving at least one of them. And then it can be in our solution. And this is actually part of how the proof that you require at least 17 givens was done, is by, and this took years of compute time, years of actual time, and even more of compute time. The way it was done was by generating every possible Sudoku solution up to transformations. There's a ton of transformations you can do that make them the same exact puzzle. But up to transformations, every single possible solution to a Sudoku, and then identifying all of the kind of what they call unavoidable sets. So like this is an unavoidable set. There's bigger ones too, but generating a bunch of unavoidable sets in each one, and proving that then you need to have a given within each unavoidable set. And there wasn't a single Sudoku solution that required fewer than 17 givens to be placed in each unavoidable set. So that is how that was proven. Pretty interesting, right? Anyway, hope you enjoyed this. If you did, then why not leave a like, subscribe, and a kind comment below.